In this problem, we are given the following circuit diagram right here, and we are asked to find I1, I2, I3, I4, I5, and I6. All are in our circuit diagram. To do this, we're going to use the mesh current method to find the branch currents. And to note, this circuit is a DC model of a residential power distribution circuit, so that's pretty fun. We're going to zoom into our circuit and look at this from a mesh current perspective. We know mesh currents, we are going to look at all the individual parts of this. So this is one part right here. This is part of Kirchhoff's voltage law, and this is the other part right here. And then we have another big part right here. These are all enclosed systems. So these three parts we're going to look at individually. First, we're going to look at this top part, and we're going to say that the current is flowing like this, and we'll just have it go this way. It can go either way, but then basically our equations would be flipped if we did it the other way. However, it should still work. So it's going to go this way, and then we're also going to have a current flowing through this part right here. We could do the same thing where it looks like this. And lastly, for this big one, we're going to have the same thing. It's going to have a current flowing through this. We just have to stay consistent with our direction. Basically, if the current's flowing through this way, it's going to be going through here and going down just as it is in our current, which we should define as IA. And I'll call this lower one IB, and I'll call this big one IC. And this IC, well, it's going to be going like this. So where current is going to be flowing through here like that. And that is our currents. So now we just got to find IA, IB, and IC. We're going to use the mesh current formulas to solve for this. First thing in our IA is our voltage right here. We know we go into the positive, out of the negative. So since this is going in the opposite direction of our current, we're going to have a negative 125 volts. Now we're going to solve for IA. All of these resistors around it, the 1 ohm, 6 ohm, and 2 ohm resistor, are in series around our current if we're just looking at this enclosed part. So that means we're going to have a 9 ohm resistor of IA. So we'll have 9 ohms subscript, or I subscript A. So this is the first part. Now we can see that it's kind of butted up against this IB and butted up against this IC. So they're right next to each other. We know that our IC, because our IC is going this way, is in opposition with our IA. Same thing with our IB. We know our IB is going to the right, while our IA is going to the left. So we're going to have to subtract these. We're going to say a minus 2 ohm resistor. This is for our IB. And for our IC, we'll have a negative 6 ohms IC. And this is all equal to 0 because the voltage inside of a closed area is equal to 0. That's rough definition of what Kirchhoff's voltage law is. So that's for IA. We'll simplify this a little bit. I'm going to move the 125 ohms to the right and then divide everything by ohms. If we do that, we are going to get this right here. And this is kind of our first equation. We have 3 unknowns, so we're going to have 2 more equations that we'll write right now. First, we're going to write for I of B. Well, we have another voltage going through here. This is 125 volts going in the opposite direction of our current. So we have negative 125 volts. Now we want to add all of the IB currents. So we're going to have a 2 ohm, 12 ohm, and 1 ohm resistor. This means we're going to have 15 ohms of our IB current. Now this is in opposition with our I of A over this 2 ohm resistor and our I of C over this 12 ohm resistor, because they're kind of, touching, so they're sharing currents, but the current's going in opposite direction. So in here, we're going to have to subtract our I of A, again, because it's going in the opposite direction of our IB. So we're going to have a minus 2 ohm, and this is IA, and then a minus 12 ohm, and this is of IC. This is also equal to 0. And now we can rewrite this the same way as we did the first time. And we've solved for our second equation. Now we're just going to look at our third equation, which is IC. We don't have any voltage in here, so we're just going to look at our resistors. These are the only parts in our circuit diagram that's in this actual portion. So we're going to add our resistors together. We're going to get 24 plus 6, 30 plus 12, which is 42. So for I of C, we're going to have 42 ohms of resistance. This is against our 6 ohm current and this 12 ohm current. Both are going in opposite directions. We can see right here and right here, and our IC is going this way. So we are going to subtract these as we have done previously. We'll have a minus 6 ohm, and this is our I of A, and then we're going to have a minus 12 ohm, and this is for our I of B. And this is all equal to 0 per Kirchhoff's voltage law. So I rewrote all of these down here, and we can see that this is kind of look like a matrix. And if you don't know what a matrix is, well, we could do this by, you know, solving for I of A, or solving for I of B, or solving for I of C, plugging this in, and this would take a while. A long time, depending on how big your problem is. I feel like this would take a while. So instead of doing that, we're going to go on Brave, Google, Edge, anything, and look up a matrix calculator. I'll have one by Symbol Lab that I use, linked below, and their website is going to look something like this. So I want to make my matrix in here, and we can see, if I move this over, we're going to have a 3x3 matrix to the right, and then we're going to have our X, Y, and Z. I'm going to replace this I of A, I of B, and I of C with X, Y, and Z. That way it'll be a little bit easier for our matrix calculator, and then it's set equal to all of these on the right side. So now I'm going to plug all this into our matrix, again keeping in mind that I of A, I of B, and I of C are being represented as X, Y, and Z respectively. So we're going to have our 3x3 here, and then it's going to be multiplied by a 3x1, and we're going to set this equal to a 3x1 as well. Now we can start filling in all of the things that we have. Now I've plugged everything in, and this is going to be the solution. Should probably turn that off later, but this is the solution that we get, and these are the steps. They're locked. I'd have to make an account for that, but we really just need the answer for our X, Y, and Z, and they give it to us right here. So I'm going to grab this, thank you Symbol Lab, and come back into our problem, paste this right here. Remember, our X is our I of A, our Z is our I of C, and our Y is our I of B. So we found all the currents flowing through each part of our circuit. Now we have to actually find the currents flowing through each resistor. Now to do this, it's kind of like a problem that we did just previously, kind of the same thing. Link below for a playlist with that and a bunch of other problems as well. But when we look at our I1 right here, it's just the current and the resistor. So it's just going to be the current flowing through it, which is I of A. We know our I of A is flowing through here in the same direction, just like this. So our I1 is going to be our I of A. These are also all of our I of A, I of C, and I of B's. So for our I1, again, it's just the same as I of A. We're going to have 23.8 amps. So that's the answer for our I1. Now we want to solve for our I4 because it's right next to it. Well, our I4 is going in the same direction of our I of A, so that is good. However, it's also going in opposition with our I of C right here. So when we write our I of 4, it's going to be equal to our I of A minus our I of C, again because it's going in opposite direction. So we're going to have our I4 is equal to our IA minus I of C. And this is going to give us 15.14 for our I of 4. Now we're going to look at our I of 2 right here. Our I of 2 is going to the left, which is the same direction of our I of A. So in our I of 2 is equal to our I of A. But it's going the opposite direction of our I of B, which is right next to it. Since it's going opposite and it's right next to it, we're going to have to subtract our I of B. That means our I2 is equal to 5.38, and of course all of these are in amps. Now we're going to look at our I of 3 down here. It's just going in the same direction as our I of B. It's not up against anything, nothing's changing the current flow, so our I of 3 is just I of B, which is 18.42. Our I of 5 is right here. It's going downwards. Our I of C is right next to it going upwards, and our I of B is right next to it going downwards. So for our I5, our IB is in the same direction. We're going to have our IB minus our I of C because that is in the opposite direction. And then we're going to get I of 5 is equal to 9.76. And lastly, we have our I6 right here. It's all by itself, just going in the direction of our I of C. So our I of 6 is equal to I of C. And that is how you do this problem, as well as the answers for it. If you want notes for this section and other introduction to circuit analysis, they'll be linked below, as well as a playlist with tons of other problems like this.